Basic Calc, these are your day 107 notes. Today we're going to be taking a look at some more tests for convergence. They're called the ratio and the root tests, and we're going to get into them very quickly here because the first page of the notes is really just a recap of what you might or might need a little bit more practice with as far as the series tests that we have. At the end of day 106, we actually have a nice summary of each of these tests, so I want to see what do you remember. Okay, so can you fill in the general rules for what we know about geometric series, the nth term test, direct comparison, integral test, and then limit comparison. See kind of what you can write down, and if it's not identical to what we wrote down on day 106, if it has the same general idea, that's of course all that matters. But I would say see if you can fill this in, and we could always talk about that next time we're in class. But let's jump right to the next page where we have two more tests. We have the ratio test and we have the root test. And we'll talk about instances in which we might apply those and see the conditions that must be true in order for a series to converge after using one of these tests. So here's the first initial condition. Suppose that we have a series and that the sequence is positive for all values of n. What we're going to do is we're going to consider that the limit as n goes to infinity of a sub n plus 1 over a sub n equals L. Okay, so we're going to take our sequence within our summation here, and we're going to consider doing a sub n plus 1, so taking, the term beyond the nth term, plugging in n plus 1, and then dividing it by a sub n. And if that limit exists, if it equals L, well, then the original series will converge under certain conditions. And here are the conditions. If the limit is less than 1, then the series will converge. And meanwhile, if the limit is greater than 1, then the series will diverge. Which brings us to, well, what are we leaving out? What if the limit equals 1? Which will happen, by the way. If the limit equals 1, unfortunately, the results are inconclusive. We can't conclude converge or diverge, so we need another test to be able to determine whether or not the original series converges or diverges. Okay, so we are going to have to do another test in that scenario. If we apply the ratio test and we're not getting the results that we expect. All right, we're going to see some similar information as it concerns the root test here. So as far as the root test goes, the initial conditions are the same. So we have a series such that a sub n is greater than 0 for all values of n. And this time that we're going to take the nth root of the sequence, a sub n. So if the limit as n goes to infinity of the nth root of a sub n equals some limit L, well, we're going to find very similar conclusions. That if L is less than 1, the series will converge. And if L is bigger than 1, the series will diverge. And if L equals 1, still inconclusive. Okay. And you're going to use this when you have something to the n power. So when you're trying to determine, in the future, which test should I use? If you have a quantity to the n power, that's when you're going to be using the root test. So how will I know if maybe the ratio test is the best option for me? Well, we're going to see that in a moment on the next page. I'll tell you what to look for in just a second here. All right. So hopefully you have that all down in your notes. If not, pause, get it down. Let's go right to the ratio test here. So for examples of the ratio test, what you're going to look for series that have factorials in them. And who knows if I'm just excited about that statement or if I'm trying to get you to look for the symbol. Aha. All right, yes, just look for factorials, and that is typically a go-to in terms of using the ratio test, although I'm sure we'll break that rule here and there, that even if it doesn't have factorials, we'll still use the ratio test at times. Okay, so what does the ratio test say? For this first example, for 2 to the n over n factorial, we're trying to decide what the limit as n goes to infinity is of a sub n plus 1. So this sequence right here with n plus 1 subbed in. So 2 to the n plus 1 over n plus 1 factorial divided by a sub n, 2 to the n over n factorial. So if this limit exists, and it's less than 1, it converges. Greater than 1 diverges. Equals 1, we're in trouble. We got to do something else. So to kind of clean this up here, let's write this as the limit as n goes to infinity of 2 to the n plus 1 over n plus 1 factorial times the reciprocal n factorial over 2 to the n. So in terms of simplifying this expression, let's do this wisely as far as we can reduce this diagonal with those base 2's there, and then the factorials will reduce as well. This is going to become the limit as n goes to infinity of, think about n plus 1 factorial is going to be n plus 1 times n minus 1 times n minus 2. And that's exactly what this is going to be right here with all of the terms. So in other words, this n factorial cancels with all of the factorial here. The only thing you would have additionally is n plus 1. Okay. So the denominator is just n plus 1. And in terms of the other parts here, when I divide those base 2's there, we would subtract the exponent. So n plus 1 minus n is now 2 to the first, or just 2. And since this reduces in this fashion, that we're now left with the limit as n goes to infinity of 2 over n plus 1, well, it's bottom heavy, so therefore the limit as n goes to infinity is 0. And since we have a limit, and it's not equal to 1, since 0 is less than 1, we know that the series from n equals 1 to infinity of 2 to the n over n factorial converges by the ratio test. Okay. So that's what the ratio test will look like. We're going to do a sub n plus 1 over a sub n. And then hopefully after simplifying and evaluating the limit, we'll have a very clear conclusion as long as we don't get a 1 there. Okay. All right, while we're practicing with the ratio test, let's see if we can apply it to the next example. Even though there's no factorials here, again, there are certainly times where maybe you can apply the ratio test and get a conclusion that makes sense. So let's take the limit as n goes to infinity of, if I do a sub n plus 1, that would be radical n plus 1 over n plus 1 is n plus 2 over a sub n, which is going to get cleaned up into, if I multiply by the reciprocal, radical n plus 1 over n plus 2 times n plus 1 over radical n. Okay. So the cleanup on this one is not as nice because I don't see the factorials that kind of nicely cancel out and those, those common base 2's there. But we do have the same quantity in the numerator, right? I mean, this is n plus 1 to the 1/2, and this is n plus 1 to the first right now. So we could write that as limit as n goes to infinity of, well, that's going to be n plus 1 to the, add those exponents. So now it's to the 3/2 power. And on the bottom, if you multiply n plus 2 times radical n to the first times n to the 1/2 is going to be n to the 3/2 plus 2 times radical n, or 2n to the 1/2 if you want to just write everything with fractional exponents. And the reason why those fractional exponents I think are kind of nice in this example is that it's easy for us to see right now that this is an equal heavy fraction. Right, the leading terms would be n to the 3/2. So if I divide the ratio of those lead coefficients, we wind up getting that the limit as n goes to infinity for this sequence is 1. And therefore, according to the ratio test, we know that this is inconclusive. Oh, man. Okay, so when the limit equals 1 after applying the ratio test, we have to do something else. So it turns out ratio test maybe was not the best choice here. But I'm going to switch over to a test that we looked at a few days ago called the limit comparison test, because we have a good comparison series to look at. Let's compare to 1 over radical n. And the reason why 1 over radical n is a good choice is that the numerator right now of radical n is n to the 1/2. And the denominator is n to the first. So this would reduce to 1 over radical n. So in terms of the limit comparison test, what we want to show is that if one of the comparison series diverges or converges, okay, and the limit of the ratio of the sequences converges, then we'll know what to do as far as making our end conclusion. Okay, so let's actually talk about the comparison series, which would be talking about the integral from 1 to infinity of 1 over radical x dx. Okay, so if we're looking at this as our comparison here, we know that this diverges by p series. So if you review what we've talked about with p series, if this exponent is less than 1 down there, we know that that's going to diverge. Okay. And beyond that, we also have to show that the limit as n goes to infinity of the ratio of radical n over n plus 1, the original, over our comparison series exists. Okay, so if this limit exists, and we've proven that this series would diverge, then the original series will also diverge. Okay, so in terms of simplifying this here, if you multiply the top and bottom by radical n, this is going to turn into, let's see, that's going to be n over n plus 1. And the limit as n goes to infinity, equal heavy there, is 1. Okay, so the limit exists and is greater than 0. Okay, that is one of the conditions for the limit comparison test, that the limit has to exist, has to be greater than 0. If that's true and the comparison series diverges, the conclusion is that the original series, which is radical n over n plus 1, diverges by the limit comparison test. Okay, so limit comparison, again, just as a recap, pick a comparison series, show that it converges or diverges, show that when you take the limit as n goes to infinity of the ratio of the sequences, that it equals a constant L. And if that's true, whatever the other series did, the series will do as well. Okay, so if this diverges, we've got diverge over here as well. Okay, a little bit more with ratio tests to come on the next page, but I think we'll save this page for class. Okay, we see some factorials there. We're going to talk about this example, which actually has a mix of x's and n's within it. And we're going to try and determine, for what values of x will that converge. Right? We know the conditions that need to hold true in terms of that limit in the end for convergence, but we're going to see how we can kind of work that in with x's and n's mixed in together. So let's take a look at the last page here. On the last page, we're going to be practicing with the root test. Because again, great candidates for the root test are examples when we have something to the n power. So if I, in this first example, apply the root test, it would say take the limit as n goes to infinity of the nth root of 1 over n to the n. And that very quickly becomes the limit as n goes to infinity of 1 over n, which is 0. Now, the same rules kind of apply when we use the root test in terms of whether or not we converge or diverge. Since the limit is less than 1, we know, therefore, the series from n equals 1 to infinity of 1 over n to the n converges. And it converges by the root test. So in certain examples, the root test can go pretty quickly for us. All we need to be able to do is evaluate a limit as n goes to infinity for the sequence after taking the nth root. And based on comparing that limit to 1, we can determine converge or diverge. All right, let's try it again for this one. I see some things to the n power. Let's see if the root test is conclusive here. The limit as n goes to infinity of the nth root of e to the 2n over n to the n. It's going to turn into the limit as n goes to infinity of, well, the nth root of e to the 2n is just e squared on top. So we have a constant. And nth root of n to the n is just n in the bottom. So that constant over n as n goes to infinity is going to 0 again. So 0 is still less than 1. Therefore, we know that the original series is going to converge by the root test. Okay, root test goes pretty quickly here. All right, last one. I see 3 to the n in the denominator, so maybe it's the best case scenario to try a root test. Let's see, limit as n goes to infinity of the nth root of n cubed over 3 to the n. Well, what's that going to turn into? The nth root of n cubed on top is going to be n to the 3 over n power Okay, bottom is just 3. And what we need to decide right now is, what's the limit as n goes to infinity up top? Okay, what is this approaching as n gets larger and larger and larger? So see if you can do this the rest of this one. So I said to try it actually, but I've gotten you a little bit of an initial setup with the root test here. Determine what this would approach as n gets larger and larger and larger. And then therefore, once you've gotten to that result, determine in the end if this converges or diverges by the root test. So I'll let you finish the rest of that one. That's pretty much it for day 107 here. More to come with ratio and root tests. And guess what? There are even more tests to determine converge or diverge in the future. We're getting close to the end, but we still have a few more to go. All right, have a great rest of your day.